Hello, I am Kaidi Xu. Here's my project for image processing by University of Florida, and my topic is asymmetric discrete graph hashing in large-scale images. So, hashing techniques have attracted considerable attention for tracking a variety of large-scale tasks in both computer vision and machine learning. The core idea of hashing is to map high-dimensional data into a low-dimension binary space with perceiving the similarity among neighbors. Hence, the high-dimensional data can be represented by a set of compact binary codes, which lead to significant gains in both storage and query speed. Over the past decade, various hashing methods have been proposed. Generally, these methods can be grouped into two main categories, which are data independent and data dependent. So, we can talk about the difference between them. The utilize simple random projection to generate binary codes, thereby requiring long binary codes to achieve good retrieval accuracy. To learn compact binary codes, an interesting number of methods focus on learning data-dependent hashing function with variable training data, based on whether utilizing the semantic information. Data-dependent methods can be further classified into unsupervised and supervised hashing. Unsupervised hashing methods such as spectral hashing, anchor graph hashing, and iterative quantization try to explore intrinsic features of data to learn binary codes without any supervision. Well, by contrast, supervised hashing methods including linear discriminate analysis hashing, minimal loss hashing, and semi-supervised hashing leverage semantic information to map the high-dimensional data into a low-dimensional binary space. Recently, supervised hashing has attracted increasing interest since unsupervised hashing methods are not able to guarantee desired retrieval accuracy via semantic distance due to the semantic gap. Meanwhile, compared to linear hashing method, a kernel-based hashing method like binary reconstruction embedding, random maximum merging hashing, and kernel-supervised hashing usually achieve better retrieval performance because they can capture the nonlinear manifold structure hidden in the data. So, to capture the nonlinear manifold structure hidden in the data, most of data-dependent hashing methods are derived from traditional demogenality reduction techniques. One popular demogenal reduction framework is graph embedding, on which many hashing methods like SH and AGH have been developed. However, there are two major bottlenecks for graph-based hashing methods. The first one is directly learning the discrete binary codes is an NP-hard problem, and the second one is that the complexity of both storage and computational time to build a graph with n data points is O(n) squared. And these two problems that we want to try to solve. So here's our approaches. To obtain binary codes, most of graph-based hashing methods utilize the relaxation and add rounding schemes, which might generate accumulated quantization error between hashing and projection functions, especially for large-scale training data. Therefore, discrete graph hashing with perceiving symmetric discrete constraints using the element-wise product of two identical discrete matrices to preserve the similarity among neighbors has been proposed to remove this limitation. To improve storage requirement and computational time of graph generation, DJH adopts one popular strategy named anchor graphs to build an approximate symmetric neighbor graph, and which we also used in my paper. here's the experiment setting. We iterate the proposed algorithm ADGH and KADGH on 3 benchmark large-scale image databases: the CIFAR10 and YouTube and ImageNet, which are all famous. The CIFAR10 database is a labeled subset of 18 million tiny images constituted of 60,000 color images from 10 object categories. And here's the results. So, this is the Hamming ranking performance on the CIFAR10, which I introduced before. And compared to the unsupervised hashing method, like an LSH, SH, and AGH 1 or 2, and DGH, the supervised hashing method ADSH, SDGH, LINV, and COSDISH, fast hashing KSH and SDH can obtain better retrieval accuracy. We can see this is really better because they utilize the semantic information to encode each image into binary code. And this is the training and test time on CIFAR10. So ADGH outperforms COSDISH, probably because COSDISH divided the training data into 2 parts to produce binary codes, thereby losing some semantic information. ADGH takes less training time. You can see here. Cost to produce relatively long binary codes than COSDISH. Since the optimization procedure in COSDISH calculates the binary codes bit by bit, ADGH achieves better retrieval performance than SDGH with shorter binary codes. The number of bits is smaller than the number of classes, of course, probably because the asymmetric discrete constraint can better pursue the similarity of affinity matrix than the symmetric discrete constraint. So ADGH has superior retrieval accuracy, including both MAP and precision to LINV, probably because it can joint learn binary codes and the projection matrix. Moreover, ADGH consumes less training time than SDGH and LINV because of the asymmetric affinity matrix and its efficient optimization procedure. So, more details you can see in my paper, and that's all. Thank you.